Hello, everyone. Welcome. My name is Damien, and I'm here to uh, introduce Amazon MSK if you're not familiar with it, and how to um, take your workloads that are based on Apache Kafka and migrate them into Amazon MSK so that you can eliminate or alleviate the overhead of running Apache Kafka on your own. The agenda for today is here. We're going to walk through Apache Kafka at a very high level. It'll be a very brief intro. We're not going to go into great depth. My assumption is that you're already running Apache Kafka and you're familiar with it. And we'll also cover some of the challenges that you might be facing with Apache Kafka in production and how Amazon MSK addresses these challenges so that you don't have to. Last week, we made a few announcements, namely general availability, and we're going to walk through those announcements and also provide a little bit of depth behind those in this webinar. And then finally, we'll close with a brief introduction on MirrorMaker, some best practices, and also how to use MirrorMaker to migrate or replicate your Apache Kafka workloads. Get started with Apache Kafka and why our customers love it. First, here are some high-level examples of use cases for Apache Kafka. Most customers, when they use Apache Kafka, they use it as a streaming data store. And what that means is they can take events, logs, etc., and stream it into a Apache Kafka cluster, and then have applications that are listening to these events as they come in, reading from Apache Kafka, and processing those events in logs in real time. And so the couple of use cases are real-time web and log analytics. So we often see customers driving clickstream events into Apache Kafka for either real-time analytics of those events, so that you can provide your customers that are within those web environments with a better experience, or if you're just trying to ingest and capture those events and drive them into some downstream data store, that's very common as well. We also see many customers ingest logs using Apache Kafka, so they're taking application logs or machine logs, EC2 logs, driving those logs off of those devices and using Apache Kafka as a durable, reliable store for those logs, where those logs are then read from Apache Kafka in real time and processed, transformed, and sent to a downstream store. Many customers are also building algorithms on top of Apache Kafka, where they're detecting anomalies, for example, where you might have a VPC flow log that is anomalous, and applications are reacting to those logs in real time. We're also seeing many customers use Apache Kafka for messaging. And the reason is that when data flows into Apache Kafka, it is stored in a queue format, in that data is accepted in the order it was generated, and then it's also processed in the order it was generated. And messages can be queued up within Kafka's partitions. And what we're also seeing is these customers, while they're using Apache Kafka for messaging to get started, they're also expanding the use cases for Apache Kafka on the same messaging pipelines that they have. Maybe they want to expand into real-time analytics, or do some different transformations, or have many different applications that are reading from Apache Kafka and processing those messages. We're also seeing many customers use Apache Kafka for transactions and also event sourcing. The semantics that Apache Kafka provides, like exactly once, enables customers to maintain transactionality and item potency throughout their architectures, using Apache Kafka as a buffer between the applications that generate the transaction and the applications that need to process the transactions. Event sourcing is also very common, and this ties into the decoupled microservices use case, where people are gathering all events within an organization and using Apache Kafka as that ingestion and data store for those events. And they are building decoupled microservices and other applications on top of Apache Kafka and using it as an event store throughout their organization. And finally, another popular use case is streaming ETL, so extract, transform, and load, rather than batching data and then performing the ETL process on batches of data. What we're seeing is many customers are doing this on a record by record, event by event basis, using Apache Kafka applications. So you could take a stream of events and then transform those in real time as they come into Apache Kafka, and then deliver those events to a downstream data store like S3 in the format that is required. And then using, if you consider the latency impact of doing that, you can actually get the data transformed and in a usable format much quicker than you would otherwise if you were to use a traditional batch process to transform your data. So these are just a few of many different use cases that we're seeing for Apache Kafka. And here's how Apache Kafka works at a very high level. On the left, you have producers, and on the right, you have consumers. And in the middle is what makes Apache Kafka run. And that is a group of EC2 instances called brokers. And brokers are essentially the hardware that is storing the data and serving the reads and writes from your producers and consumers. Data comes in, and Kafka replicates it automatically across the brokers if you have decided to use a replication factor of more than one. And it's also the state of those brokers and the topics and Kafka itself is maintained by Apache Zookeeper, which is actually a separate cluster that runs alongside an Apache Kafka cluster. Each Kafka cluster, in order to use it, requires that you create topics, and a topic is a logical group of partitions. And producers write to specific topics, and then they can partition data using a partition key to maintain order within for a specific identifier. For example, if I wanted to partition records based on my name or a user's name, you could do that using a partition key that maps to the name of the user. And as you can see in this case, if a producer is writing to partition 1, the data is kept in the order it was generated, so from the oldest to newest, and the same goes across the other partitions within the topic. Similarly, on the other side, you have consumers, and a consumer group is a group of worker threads that each process they work in parallel to process all data within a topic. So a consumer will map one-to-one to one partition in a topic, and it reads data in the order it was generated, starting from the oldest to the newest record. As you can see in partition 1, the consumer has read record 4 and is moving on to record 5. And Kafka manages offsets, so it knows where the consumers are in terms of where they're at in reading the data within a partition. So it knows how to handle failures when they occur, because if a consumer didn't read a record, it knows where the next consumer can pick up from. Excuse me. There are a number of challenges that our customers face when they're running Apache Kafka on their own. First is it's difficult to set up for production use cases. When you consider the actual getting started process for Apache Kafka is pretty straightforward. You spin up Apache Kafka on EC2 instances and then separately provision Zookeeper, and you can within minutes you can create a cluster and get started pretty quickly. However, if you're setting up for production, that's a totally different story. You need to have automation in place that handles failures. You need to consider the patch management requirements for your infrastructure. You need to have on-call engineers that are reacting to different metrics and alarms as they come up. You need to scale your clusters. You need to manage the hardware lifecycle throughout your use of Apache Kafka. So there's a lot of automation and muck that our customers have to set up in order to get Apache Kafka running on their own for a production use case. A lot, and this also makes high availability harder to achieve for customers if they are having to handle operational events and other things that they're not used to dealing with. So, for example, if they haven't automated the processes within a Kafka cluster, then the customer is going to find it harder to recover from an event, and therefore make it harder for them to achieve high availability within their cluster. Apache Kafka also doesn't come with a console or metrics out of the box. It's difficult to scale, not only on the storage side, but also on the broker side. If you want to scale out a cluster, you have to add brokers to a cluster and then migrate partitions. Now that's the same with MSK for the time being, but that's something that we will be solving over the near future. Also, if you want to build in AWS integrations into your Apache Kafka cluster, your teams are going to have to develop those on their own. And then finally, if you add this all up, all of this requires specialized skills. Most commonly, site reliability engineers need to, or are those folks who are deployed to architect Kafka, make sure it's up and running, operationalize it for production use cases. And for what we've discovered is a lot of customers, they don't have this talent internally, or they just don't want to deploy their engineers in a manner that is not in line with their core business focus. And so what we've also seen is that a customer's Kafka usage is a function of the talent that's inside of their organization that is skilled with Apache Kafka and its operations. So these are some of the challenges that Amazon MSK is addressing or will be addressing over the near future. Amazon MSK is a fully managed, highly available, and secure service for Apache Kafka. And what we do is we make Apache Kafka production ready for anyone who wants to spin up a cluster within the Amazon MSK service. And what this means is that anybody in your organization can access their own dedicated Apache Kafka cluster with a few clicks in the console, not have to worry about the operational muck that is required to get a Apache Kafka cluster ready to go for production use cases. We're also using best practices that are widely known throughout the open source use of Apache Kafka, and also through our experience running massively scaled fleets for AWS. And we're using those best practices within the design and automation of Amazon MSK. And what this does for you is it allows you to focus more on the applications that really matter for your end customers and less on the infrastructure, because your business, in order to continually innovate, you need to continue focusing on what matters. And what typically matters is what your customers want you to build and offer as an end product. And finally, because we are running open source Apache Kafka for you, we are committed to improving and driving the success of Apache Kafka within open source, because not only is it important for you to have a great open source product that we run, it also is important for our service to take the feedback that we get from running your clusters and from you and driving that back into the open source community. Getting started is pretty easy. Within a few clicks, you can get a fully compatible Apache Kafka cluster up and running. We currently support 2 versions, and we're going to be rolling out new versions shortly. The 2 versions are 1.1.1 and 2.1.0. As you would expect, we offer an AWS management experience along with AWS APIs that you can use for provisioning. Clusters are set up automatically, and you simply just select the types of brokers, the quantity of brokers, and the amount of storage you want to provision per broker. And we'll take that information and deploy the cluster. And all of this comes with the capabilities to create and tear down clusters on demand. There are no commitments or investments required to get started, or penalties if you turn off clusters. Zookeeper is a fully managed component of each Apache Kafka cluster that you provision within MSK. And we manage Apache Zookeeper under the hood with each cluster. You don't see it. Your clients can continue to connect to it, but you don't need to provision for it. We take care of that cluster for you. It's highly available. We provision dedicated nodes across 3 availability zones with each cluster. It's fully managed, and finally, there's no additional cost. It's included with each cost, or excuse me, it's included at no additional cost with each cluster you provision. We designed Amazon MSK to provide private connectivity always, at least until we provide you with a feature in the future that provides public connectivity. But for the time being, the only way for your clients to connect to a Amazon MSK cluster is through a private connection inside of your VPC. And the way we do that is we use ENIs, which you'll actually see when you provision a MSK cluster. We will be creating ENIs within your account and using those as the bridge between your clients and the brokers and Zookeeper within an Amazon MSK cluster. Pricing is all on demand, and it's all prorated. So if you spin up a cluster and tear it down within a minute, you're only paying for the seconds that you use. Broker and storage pricing. Broker pricing starts at 21 cents an hour for an M5 large, and storage starts at, it is 10 cents per gigabyte month and both of these rates are in the US East 1 region. There's no charge for data transfer if you are using replication within a cluster. So we encourage our customers to replicate data for high availability, but the data transfer, if you do choose to replicate within the cluster, the data transfer cost from that is included. You do not pay for that separately. And you also do not pay for data transfer between the brokers and Zookeeper nodes. You will pay for the data transfer in and data transfer out of a cluster. So here's a breakdown of how performance meets costs. First, it's important to note that the performance that you will see using MSK is identical to the performance that you would see running an EC2 cluster on your own, or a Kafka cluster in EC2 on your own. And so what we've done here is we've provided some benchmarking that lets you see what you can get out of a M5 extra large cluster, and then not only in terms of throughput, but also latency, and then translate that into cost. And our hope is that you can use this to not only select how much you want to provision for, but also it'll also give you a sense of how much you're going to end up paying on a per gigabyte basis. So let's take a look at a few of these rows. Let's start with row 1. In this example, we had a one consumer, one producer test where we were targeting 500 megabytes a second with 1 kilobyte records, and we're driving this into a M5 extra large MSK cluster with 15 brokers. And what we're able to see in actuality, we're able to get 414 megabytes a second out. So this shows you that we didn't have enough capacity provision in this example, but you were able to get 414 megabytes a second through a M5 extra large cluster, which is a lot of throughput. However, the latency that you're getting in this example isn't quite that great. So if you're also looking to provide a low latency experience for your producers and consumers, you're probably going to want to provision a little bit more or drive a little bit less throughput on average for this cluster. Because as you can see in row 1, the latency is quite high. On P99, the P99 latency was over 200 milliseconds. And then finally, the dollars per gigabyte in this example equated to 3.8 cents. And this cost includes not only the cost of the cluster, but also includes the data transfer cost that you would end up paying on your own from data in and data out of the cluster. So let's look at line 10, which is the row 10, excuse me, the one that I have highlighted here. Well, at least highlighted the latency. And I highlighted that one because most of our customers have latency sensitive applications. And what we normally see is most customers designing for P99 latencies below 100 milliseconds. And that's the threshold that I used in this this example, and which is why I highlighted it as such. But we were able to get 125 megabytes a second through an M5 extra large cluster of 15 brokers, and which is about 8 megabytes a second per broker, and also hit our latency target, which was being under 100 milliseconds P99. And finally, this translated to a cost all in of about 4.8 cents per gigabyte. So you can use this as a table to get you started. So if you want to work backwards from your throughput, you can use this to figure out how many brokers and of what type that you should provision for an MSK cluster. And finally, as you can see, on the dollars per gigabyte, the cost ranges from about 4 cents to 7 cents per gigabyte all in, and that includes the data transfer in and out of the MSK cluster as well. A common question that we receive from our customers is Amazon MSK compatible with XYZ? And and a good way to think about it is we are offering a fully compatible product because we are running open source versions of Apache Kafka. So any framework and tool that is compatible with the open source versions of Apache Kafka, it's also going to be compatible with Apache Kafka on MSK. So this means that you still get to run Kafka Connect, MirrorMaker, Kafka Streams, schema registries, REST proxies, and Burrow or another. Those are also popular tools that our customers want to run alongside an MSK cluster. However, there's there are a few things that we don't allow, and that is the tools that upload jar files to brokers, and a few of those tools are listed here. Now, there's a number of tools out there that we do not provide managed support for, like the schema registry and REST proxy, but you can run those tools alongside a cluster. Amazon MSK was launched in an open preview at reInvent this last year, and we're excited to announce that it is now generally available. And general availability means that it's available in 10 AWS regions. We also announced support for 3 additional regions. The Frankfurt, London, and Paris regions were made available for MSK last week. We also added a stack of new features for MSK for general availability. First is TLS encryption in transit, and this is also a feature that's enabled by default and is a you can use it to encrypt data between your clients and the cluster, and also use it to encrypt traffic between brokers. We shipped a mutual TLS client authentication feature so that you can have fine-grained control over the clients that authenticate to an MSK cluster. There's a 99.9% availability SLA, and the service is also HIPAA eligible. You can now scale your storage within a cluster and also load custom Kafka configurations. So if you have a different configuration that you'd like to load, you can quickly and easily do that through our CLI. You can also tag and use tags to control the IAM policies and how they're applied to an MSK cluster. And then finally, we will be adding CloudFormation support over the coming days. There are a number of customers already using Amazon MSK. Here are a few, and as you would expect, the common theme here is reduction of overhead, and also which translates to the customer accelerating their own product's time to market, because they can now spend more time focusing on the applications. So here's a console snapshot of the new encryption feature for in-transit encryption, and you can separately enable encryption between brokers using in-cluster encryption, and you can also enable client to broker encryption as well. Mutual TLS authentication uses private certificate authorities from the AWS Certificate Manager service and allows you to deploy those to MSK clusters. And when those are deployed, we're using those to authenticate clients using the client's TLS certificate that they're presenting when they are connecting to a cluster. So the process goes like this. You create a private certificate authority within the AWS ACM service. You will then enable authentication within the MSK cluster, select the certificate authorities you'd like to deploy to a cluster, and you also want to make sure that the consumers and producers are configured with a TLS client certificate that has been issued by the root certificate authority that you have selected. And finally, you can take the principal, create an ACL or an access control list within Apache Kafka, and use the DNAME of the certificate, the TLS certificate, as the principal of the ACL, so that you can tie authentication and authorization together. You can also deploy custom configurations to new clusters. We will support updating existing clusters in a separate launch, and that's coming soon. And then if you need to add storage to your cluster, you can, in a few clicks in the console or using the CLI, you can scale up the amount of storage you provisioned on a per broker basis. And finally, the cluster tagging and tag-based IAM permissioning is very useful for customers if they want to use tags for cost allocation purposes, or use tags to control who and what can make the API calls within Amazon MSK service. So here's a list of configurations that you can now tune for Amazon MSK, and that's on the right. And you simply just provide a text file with your configuration details and load that to a cluster. Currently, this is only supported in the CLI. We will be announcing console support in the next few weeks, but you can get started today using the CLI and deploy your own custom configurations there.
I have Rajiv Chakrabarty, a solution architect from AWS, to walk you through MirrorMaker best practices and a demo.
Well, thank you, Damien. My name is Rajiv Chakrabarty. I'm a specialist SA covering Kinesis and managed streaming for Kafka. I'm going to talk about MirrorMaker version 1. So Kafka's mirroring feature makes it possible to maintain a replica of an existing Kafka cluster and also migrate an existing cluster to another like MSK. The diagram here shows how to use the MirrorMaker tool to mirror a source Kafka cluster into a target Kafka cluster. The tool bundles both consumers and a producer together and uses a Kafka consumer to consume messages from the source cluster and send those messages to the target cluster using an embedded Kafka producer. You can have multiple consumers, but there's only one producer. Data is read from topics in the source cluster and written to a topic with the same name in the destination cluster. If you have auto create topics enable set to true, then MirrorMaker will create the topics for you in the destination cluster. However, it uses the cluster default config to create those topics in the destination. To increase throughput and for fault tolerance, you can run many such mirroring processes across the same or multiple machines. One important thing to remember is that the origin and destination clusters are completely independent from each other. Consequently, they can have different topic configurations with different numbers of partitions, and most importantly, the offsets may not be the same. It depends on when the MirrorMaker process is started. Further, producer retries can make the offsets different as well. However, the message key for partitioning is maintained, so order is preserved on a per key basis. MirrorMaker can be used to replicate events between on-premise or self-managed Kafka clusters on EC2 instances and MSK clusters, or between MSK clusters themselves. So this is a sample command for MirrorMaker version 1. You can configure both the consumer and producer properties of MirrorMaker, just like you would for Kafka producer and consumers in general, and control the number of consumer threads that MirrorMaker uses by configuring the num streams property. As a rule of thumb, pick a number to match the partition count in the source cluster. Till Kafka version 0.8, MirrorMaker had multiple consumer and producer threads, the number of which could be configured independently. However, with Kafka 0.9 and above, MirrorMaker changed to having a single producer, while the number of consumers is still configurable. So, to increase the number of producers and increase producer throughput, start multiple MirrorMaker processes. You also have to specify a whitelist or blacklist of topics, but not both, using the Java-style regex notation. Kafka supports multiple comma-separated regular expressions. Now let's discuss some best practices for MirrorMaker. First, run the tool in the destination. If MirrorMaker is run at the source cluster and events are buffered in the producer and there is a network issue, depending on the MirrorMaker settings for the producer, there could be a chance that events could be lost. While if it is run at the destination and a network event happens, the messages are still available in the source cluster. However, if encryption is required, then run it at the source. Encryption introduces some overhead, and the overhead is more for the consumer than the producer. So if the destination cluster is distant and you need encryption in transit, while the consumer can consume from the local source cluster without encryption, then run it in the source. Further, to avoid data loss, auto commit should be turned off at the source so that MirrorMaker can control the commits, which it typically does after it receives acknowledgement from the destination cluster. If ACKS equals all is set for the producer, which essentially means that the broker will send the ACK to the producer after the message has been replicated to all in-sync replicas, and the destination cluster has the min in-sync replicas setting to more than one, that would mean that the messages are persisted on more than one broker at the destination before MirrorMaker commits the offset at the source. If order is important, then either retries should be 0, which does not make sense in production scenarios, or max in-flight connections should be set to 1, to ensure the batches sent out are not committed out of order if one batch fails in the middle. This way, each batch sent will be retried until the next batch is sent out. If max block millisecond is not set to max value and the producer buffer is full, there could be data loss depending on some of the other settings. With it set to max value, it would block and back pressure the consumer. To achieve high throughput, increase the buffer.memory setting if memory is available. Increase the batch size so that more records can be sent out in one batch, but also tune the linger.millisecond setting to allow the batches to fill, which in turn also allows for better compression, less network bandwidth usage, and less storage on the cluster, so more retention can be provided. You might have to experiment with these settings to get the best performance. Keep an eye on CPU and memory usage as well. Some more best practices. So typically, it requires more than one consumer to saturate a producer in MirrorMaker. So have multiple consumers, and if so, have them first on different machines to provide high availability, and then scale individual machines up to having a consumer for each partition and consumers equally distributed across machines. For high throughput ingest and delivery, tune the receive and send buffers, which could be too low at default. For maximum performance, total number of num streams should match all of the topic partitions that MirrorMaker is trying to copy to the destination cluster. When running MirrorMaker on multiple machines, the configurations have to be copied to each machine and kept in sync. To do that, it might be best to use CloudFormation and other config management tools like Chef and Puppet to make sure the configurations are in sync, or use a shared file system like Amazon EFS, the Elastic File System, to keep them in sync. One other way to ease the management of MirrorMaker is to use containers. Containers provide an easy, scalable, and cost-effective way to scale the throughput of MirrorMaker and can be used with other AWS services like Amazon ECS, AWS Fargate, and Amazon EKS. Now let's talk about some of the limitations of MirrorMaker version 1. As discussed before, it does not replicate topic configurations. If auto-create topics enable is set to true in the destination cluster, it would auto-create topics that don't exist, but use default configuration in the destination cluster. This would cause the configuration to diverge. The recommendation is to set auto-create topics enabled to false and manually create the topics with the appropriate configuration in the destination cluster. The downside to that is that any further changes have to be manually replicated as well. Of course, you can potentially have a jar file that could periodically check for new or existing topics that have changed configurations and move them. Also, message offsets can be different. If MirrorMaker is started right after a topic is created and before any producer sends messages, it is possible that the offsets could match. However, producer retries could alter that. Consequently, there are no guarantees that the offsets would be the same. So with MirrorMaker version 1, it is not recommended to use it for failover and failback. Consumers on the destination cluster cannot directly depend on finding the same offsets. With regards to whitelisting or blacklisting of topics, they only support Java-style regex, and any changes would require MirrorMaker to be bounced. Some more limitations. So the configurations across multiple MirrorMaker machines, as we have talked about earlier, has to be manually synced, or configuration management tools employed, or shared storage used. It also does not support dynamic configuration changes, so MirrorMaker has to be restarted for any config changes. Also, rebalancing of the consumers in MirrorMaker pauses the replication, which can cause latency spikes, which in turn can then cause a chain reaction of further rebalances. So with all of these limitations, how do we handle things? There is MirrorMaker version 2 on the way. So MirrorMaker version 2, which is KIP 382, is currently in accepted state and is actively being worked on. You can go to the wiki mentioned on the slide and read about it. It addresses many of the limitations of MirrorMaker version 1. For example, it uses the Kafka Connect framework and detects new topics, partitions, etc., and moves them, syncs topic configurations, emits offsets required for consumers to start consuming from target clusters with offset translation, and this allows for high availability and disaster recovery scenarios. And there are a bunch of other benefits as well. So please go ahead and take a look at this and make sure that once it's available, that you move to MirrorMaker version 2. So with that, here are some of the steps that will be involved in migrating to MSK using MirrorMaker version 1. So first, create an MSK destination cluster. Then second, start MirrorMaker from an EC2 instance within the same Amazon VPC as the destination cluster. This is important for reasons that we've discussed earlier. Once you start that, keep inspecting the MirrorMaker lag. And I'll show you in a demo following this on how you can do it. And once MirrorMaker has caught up, stop all producers and consumers and then point them to the new MSK cluster using the MSK cluster bootstrap broker value that you can get using the CLI or the console. And then finally, shut down MirrorMaker. So that would be a process by which you can go ahead and migrate your existing cluster to MSK using MirrorMaker version 1. Okay, so let me get to a demo. I'm going to do this short demo of MirrorMaker version 1. I have everything set up already. I have a CloudFormation template that sets up a new VPC, one public subnet where the EC2 instance hosting MirrorMaker runs and has Kafka also installed. Also, it creates 3 private subnets across 3 AZs where the 2 MSK clusters, one that acts as a source cluster and one that acts as a destination cluster, is hosted. It also creates 2 security groups, one that is used for the MSK clusters and one for the EC2 instance. The security group for the MSK clusters allows traffic from the security group for the MirrorMaker EC2 instance on the Kafka broker and Zookeeper ports. The EC2 instance is a number of shell scripts that run the various commands. Let me switch to the demo. Okay, as you can see, there are a number of shell scripts here. There is the Kafka mm.shell script. This is to start MirrorMaker in the background. The next is the Kafka dest console consumer.shell. This is a console consumer. I'm starting to consume the replicated messages from the destination cluster. This is to show that MirrorMaker successfully replicated the messages. The next one is the Kafka producer perf test.shell, which is this one. This starts a producer performance test and sends a bunch of messages to the source cluster. And then there is the Kafka consumer groups.shell. So this this shell script runs the Kafka consumer groups command in the source cluster, which shows all the consumers in the consumer group for MirrorMaker, the partitions in the source cluster they're consuming from, and the lags from the end of the log. So this is the command that you would need to run to identify the lag for the consumers. And then finally, there is the Kafka dest consumer groups shell, which runs the same command in the destination cluster, which shows the lags for the console consumer of the destination cluster. So I've already produced some messages to this topic earlier. So let's check the current offsets by using the Kafka consumer groups command. So as you can see, the current offset for the commit log is at 200,000, and the consumer group, which is for MirrorMaker, is also at that offset, so there is no lag. So at this point, I'm going to first start start MirrorMaker in the background. Followed by the destination console consumer. Next, I'm going to go ahead and produce some messages into the source cluster. So you'd see that it sends about a bunch of messages there. So a total of 150,000 records have been sent. Then let's check the MirrorMaker offset again. As you can see that the commit log offset has moved to 250,000, and the lag is about 50,000 for MirrorMaker, the consumers in MirrorMaker. So typically by default, MirrorMaker would send messages, would ask the producer embedded to send messages every 50,000, every 60 seconds. And so you would see that this lag would catch up. Let's now we have the console consumer in the destination cluster also running. So let's take a look at what that is. So I'm going to run this command. So as you can see that it is catching up, and one of the reasons that this looks like it is ahead of MirrorMaker is because MirrorMaker, like I said, it sends the sends the messages every 60 seconds by default, and then it waits for it to come back, and then updates the offset in the source cluster. But this clearly shows that MirrorMaker is actually replicating the messages to the destination, and there's a consumer running in the destination which is actually getting those messages. So I'm going to run this again. It's getting close. Let's run it for the source cluster one more time. As you can see, MirrorMaker is now caught up as the lag is now 0. Okay, so that brings us to the end of the demo. And if you have any questions, there will be a time to ask them. And that brings us to the end of this webinar. Thank you.